I would like to pass over to Michela Morese, who's the Executive Secretary of GBEP, to give us a brief introduction to our work. Over to you, Michela.
Thank you. Thank you very much, Connie. Good afternoon, everyone, and welcome to this webinar on biochar systems for sustainable agriculture. Well, I would like to thank you all for being connected to this event, and I very much look forward to hearing the presentation of our keynote speaker today, Professor David Chiaramonti, who's an old friend and colleague of us and of the GBEP family. As you know, this webinar, and as Connie mentioned, this webinar is organized by the Global Bioenergy Partnership, GBEP, as part of our program of work. And as you may see from the slide on the screen, for those of you who are not familiar with GBEP, it is an international initiative established in 2006, mainly working on sustainable bioenergy for sustainable development, climate targets, and food and energy security. And we have on the screen the 80 members between partners and observers, mainly governments and international organizations. FAO is one of the founding partners of GBEP. Since 2006, since its establishment, has strongly contributed to its program of work and is also hosting its secretariat, which is us, organizing and coordinating all the activities and program of work of the partnership, including this webinar. If you could go next, Connie. Thank you. So sustainability, since the beginning within GBEP, has always been considered as key, because we've been aware since the very beginning that bioenergy presents excellent opportunities, but not without challenges. And in this sense, sustainability is key to take out the best of the opportunities. In light of this consideration, GBEP has been working and is still working on sustainability in order to give guidance and tools that could be useful to do sustainability assessment of bioenergy production. And in light of this, has developed something which is considered the most widely recognized and agreed set of indicators for the assessment and monitoring of bioenergy sustainability. Next. So this is the set of 24 sustainability indicators that the Global Bioenergy Partnership has developed, further to a long process of technical discussions and then agreements. This set of indicators is applicable to any type of bioenergy. It could be gaseous, liquid, or solid. And as you may see, it's the number of indicators, 24, it's equally divided under the 3 pillars of sustainable development: environmental, social, and economic. And this is also meant to be a strong political message from the GBEP family, from the GBEP network, in the sense that sustainability can only be achieved if equal importance is given to the 3 pillars of sustainable development. Of course, in this summary table, you only can see the titles of the indicators, but for each of these 24 indicators, a full methodology guidance is available. And these indicators have been measured so far in 15 countries all over the world. And we have collected all the lessons learned from these projects on the measurement of these indicators in several countries. And we've very recently released an implementation guide, including additional guidance for the use of the indicators for sustainability assessment. Well, with this webinar, we would like to highlight and discuss the main benefits of biochar in all its related steps, both in terms of production phase, which involves the use of agricultural residues for bioenergy production, and in terms of its final use as soil amendment, with all the positive aspects that may imply in terms of improved soil quality, crop yield, biodiversity, and carbon sequestration. Before I give the floor back to Connie, I would like to say that this biochar discussion today seems to be extremely timely to me, because it seems that the current crisis, both in terms of pandemic and in terms of climate, would force countries to make themselves less vulnerable to imports, and these would lead to shorter supply chains and greater emphasis on self-sufficiency in food and energy. And sustainable bioenergy, including biochar practices, will have a role to play, not only in terms of short supply chains, but in particular in terms of sustainability, also as a contribution to achieve climate targets. So now I would like to give the floor to Connie, that will mention the GBEP work in the context of which this webinar is organized, and will also introduce our keynote speaker. Over to you. Thank you.
Thank you, Michela. So as Michela alluded to, this webinar is under our working group on capacity building, and specifically in the our activity group on biogas. Now you might be asking why a webinar on biochar systems under an activity group on biogas. Well, that's actually one of the things that we'll be highlighting in this webinar today, which is the synergies between biochar and biogas systems. And Professor Chiaramonti will also be giving us a general overview of biochar, the technologies, the characteristics, and also the potentials for carbon capture and storage. I'd also like to say that we have also noticed that actually one webinar is definitely not enough to cover all the aspects of biochar, and that there's also a lot of interest in this topic. So this webinar will actually be the first in a series with a variety of speakers, and further webinars will cover other topics such as the agronomic aspects of biochar, interactions between biochar and soil, organisms and water, and also biochar supply and demand. And we'll be giving out further details of these webinars when we share the recording of this webinar. So now the only thing left for me to do is introduce our speaker for today. David Chiaramonti is a full professor of systems for energy and environment at the Polytechnic University of Turin, and he has many years of experience in bioenergy and the bioeconomy. Recently he turned his attention to biochar and compost production to improve the resilience of marginal agricultural lands to climate change, store carbon, and at the same time develop less fossil dependent agriculture. So I'd like to welcome David and thank you for him to be with us today. And without further ado, I'll pass him the floor for his presentation on biochar systems for sustainable agriculture. Over to you, David.
So, thank you very much to you, to Michela, to Tiziana, to FAO in general, and GBEP for inviting me to talk about this very important line of our research. I thank you all the attendees, and I hope that you will find interesting our discussion. I will mostly focus on two topics. One is the policy related, and the other is the product and process. I understand there will be other presentation on that topics from other colleagues with whom we also collaborate, and that is a very good timing, I think, and I will try to explain why this is the right moment to discuss about that. So as an outline, I will just go through the many possible uses of biochar to focus what will be our today discussion, because we could say we could consider many different applications, and our consideration would be different in that case. I will spend a few words about soil and decarbonization, because we have to place biochar in the context today. And then I will introduce the production technology, the characteristics. I will try to explain that biochar should be tailor-made in the way to the local conditions of soil, climate, and so on, so to better perform. And I will close with some reporting some experimentations we're doing in the combination of biochar and digestate from anaerobic digestion in the context of sustainable, more sustainable agriculture. So I start with what is our thesis. So you know where we want to go, what is our point of view. To our view, after many years of having been working on thermochemical conversion for liquid, gases, solid products, as Professor Mike Antal from the US was always saying, biochar is really a multiple win approach because of a number of reasons. First of all, is a cost competitive evidence base. It means I can measure my performance, my results, evidence-based methods, not just to sequester carbon, but also to use in a very interesting way this carbon, which is a huge replication diffusion potential. It is doable. It can be fed with many residual feedstock and many processes, even that if slow pyrolysis actually the dominating and the most appropriate solution probably. It's a mature technology, so I can down or upscale the process quite easily. It can be key to improve resilience of poor agriculture. This is our special focus. The land that is going to be abandoned or under marginalization, also integrated with sustainable rotation or agricultural models. In that sense, we differ from the past focus in the initial years of biochar R&D, which was mostly focused to this as a method to improve the yield. Our main goal, as I will show, is to have a method to keep the land productive, the socio-economic conditions alive, running well, and at the same time having other benefits. Yield improvement could happen, of course, but it's not really the only and main focus for that. It can be very cost effective. I will make an examples for biofuel production compared to offsetting, in the case of aviation, the cost of an airline has in terms of GHG reduction targets. And you will see that's very, very, very interesting. Last point, as I said, it can be very well integrated with anaerobic digestion and digestate, being synergic and not in competition. So we will conclude commenting about the economic value of this carbon. It has to be recognized is particular to the primary sector, to the farmer, that are carrying out this multiple benefit work. We will come back to this later. As I said, biochar is a very fashion word today. It can be adopted for many, many different applications. I mean, animal feed, food, even wastewater treatment as activated carbon, food preservation, other system of preserving transportation in boxes, for instance, as moisture absorption system. It can be used in litter, caddy litter for cats, textiles, paintings, cosmetics, even building, bricks made with or containing biochar. They have been. Anyway, all these are very different products. The process will be different. The feedstock also will be different. So, you know, we have to focus our attention to the application we have. And also we have to recognize that many of these applications were already using charcoal. And the use of the term biochar is, to me, a bit excessive even, because it's not new. I mean, activated charcoal is being used forever. It's not a new thing. The biochar instead in the soil is quite our main focus. Let me just try to move this down. Okay. So we are discussing about the use of a product in the soil. So soil is our target. We have to know what we're talking about in that sense. I'm pretty sure that in FAO area, you know even much better than me, for sure. But I want to focus a second on the policy part, and particularly for Europe, but it's a global consideration. Well, actually, the soil is a focus for many regions in the world. We are aware we have big problems. We had many reports. These are two examples. One on the right-hand side from the European Environment Agency based on JRC data, even claiming in the worst scenario that we will reduce by 50% wheat, corn, and sugar beet production in 2050. Even if it's not 50%, in any case, it's really a huge reduction we have ahead. But also, we have the European Court of Auditors that, by definition, is reviewing European policies, which is commenting on this, saying that the European Union is not doing enough for this sector, and that a strategy on EU level strategy on desertification and land degradation is lacking, is missing, and our commitment to achieve land degradation neutrality in Europe by 2030 will deserve more attention, more focused policy. That's a very important document. So policy-wise, we have a good environment to discuss this topic, and also in the EU Green Deal just released, we do have the soil in 6 out of 9 of the Green Deal goals, as JRC recently remarked in a public seminar. So we have to push in this direction to improve soil condition and to get healthy soil, and there's a specific mission in Europe that is dedicated to soil. Finally, as introductory point, the other is decarbonization. Since Paris COP21, we know that we must remove CO2 from the atmosphere. In other words, as commented by various operators, in that case is Professor Henderson, we have to remove carbon from the atmosphere if we want to achieve our goals 1.5 or 2 degrees maximum increase. However, so far we focus on neutral, on renewable, on neutral carbon actions because of many reasons, because these are renewable energies, there are incentives to that, there's support and so on. The cost for carbon removal is much higher. And this is where biochar can have a big role to play at very good economic conditions, if, of course, policy is following, because all these sectors are policy driven. So whatever we decide to do in the energy or in the agriculture sectors, there's policy behind that steer the decision in a different direction. Recently, on natural sustainability, the group of Bossio and other colleagues published this very interesting report that has been well visually summarized by Carbon Brief that claims some 5.5 billion tons of greenhouse gas a year that can be saved from biochar. The point is that it's the second in rank, just after restoration and avoiding forest conversion. Next is biochar as potential. I don't like ranking or competing different options. What I'm interested is to say, well, there's a huge potential. Whatever it is, we have the urgency to take action to keep the climate as possible under reasonable control in the coming decades. So biochar has a big role to play, whatever it is. That's clear for many reasons. I will show IPCC later on. Also, the European Union, to conclude this part, is clearly showing how 2050 LULUCF will be as important as all the other measures. So clearly we have to put a great attention to measure that engage agriculture and forestry has means to decarbonize the environment. What is biochar? Well, biochar is the product of thermochemical conversion of several different feedstock, the main being lignocellulosic materials, woody, but also agricultural. I will show it can stay very long in the soil, but it has a number of benefits that are greatly positive for the environment. It's not new. Again, what we're talking today is how we should act to bring this to widespread use, to deploy the entire potential. It is already on sale and studied for many small application, gardening, and other very specific cases. But what we're talking today is the large-scale use of these products, so to get large-scale benefits and large-scale decarbonization. In that sense, this is not at all yet happening. I'm pretty sure many of you know Terra Preta. I remember 2005 it was presented at the European Biogas Conference by our friends from the US. A lot of work on this area, but in reality also Europe has been engaged in biochar for a long time. And if you look into the source of these slides, which is the Biochar Journal, you will find interesting thing about Justus von Liebig in the 1800s, that is the father of organic chemistry, He was working to demonstrate that Vitalins was a wrong theory, and many other very interesting things. He was a very creative person. But the specific point he was addressing was also about biochar, how this could be produced, and in particular that he was observing his huge capacity to absorb ammonia 90 times more its volume, and that can be then again separated by simply moistening it with water. It means to release. He was also a fan of agriculture in China compared to European ones, because it was the time we were releasing our organic carbon in the rivers and losing this in the sea, while he was remarking how the organic materials, manure, excreta, organic matters in Chinese agriculture was preserved and used to bring carbon back to the soil. And this was well ahead what we're discussing today. So we must know that science has a long route behind us, and we are on the shadow of the giants, as we say, but we can do small improvements. So thermochemical conversion goes through several possible processes for biochar production, the main being pyrolysis, gasification, hydrothermal treatment. But indeed, the slow pyrolysis process is the most appropriate to produce tailor-made biochar. During pyrolysis, you have always production of three products: solid, liquid, and gaseous, in the form of charcoal, bio-oil, and biogas. Slow pyrolysis maximizes the yield of biogas. But let me remark that I will not talk about renewable energy in pyrolysis, but we are all aware that at the same time I produce the biochar, I will also have high temperature renewable energy that becomes available in the form of pyrogases that can be used for many applications, even in agricultural areas, drying products, storing products, even cooling products through absorption chiller systems. So we have renewable energy available in addition, and at the same time we produce biochar or charcoal. Slow pyrolysis is normally operated between 400 and 600 degrees with a number of parameters I will come back in a moment. As regards the material changes a lot depending on the process. It changes structure from a very amorphous to a very organized turbostratic layer-based structure at the highest temperature. You move towards graphene sheet in the very extreme case, which of course are completely different technology from what we will talk today. Our main area for biochar is between 400 and 600 degrees. You can find many interesting research work at higher temperature, 800 degrees for instance, 900, but practically when you go into the real world, the industrial plants, that becomes complicated to implement just to produce the biochar. So it's important to keep an eye what is industrially possible to implement at farm scale. Here you see a nice work done by our friends from Finland. Look, it's a tomographic X-ray analysis of a small piece of willow carbonized. It's interesting to know that pyrolysis temperature is even very low, 320 degrees. I will come back to that point very soon. Anyway, you see the porous structure of the char. You will see there are two different pores, one 60 micrometer, another 12 micrometers. They fall in the area of macropores. That is important because because when you consider using this char into the soil, you have to consider this area. This is the dimension of the pores that are typically related to the plant available water. So, for instance, if I produce a very high surface charcoal through activation, so I have activated charcoal, well, actually I'm in that area of meso and most likely micropores, nanometer pores. So what happens? Happens that I can store a lot of water, but then releasing this water in the soil or to the plant, it's not easy. We have to tailor the biochar to the application, which is the use in the first centimeters of the soil for crop benefit. Of course, it is also related to the soil type, and there would be a lot to say. I'm pretty sure next presentation, I'm an energy engineer, next presentation probably will be given by colleagues more focused on the agricultural part, but indeed this is very important. And it's also important, the characteristic of the surface of the charcoal internally to the pores, and some properties that are very relevant for the cycles in the soil. Here you see a hardwood and a softwood piece, and what we do actually with carbonization is just to remove material, the hemicellulose and cellulose part, and keep most of the lignin and some other components, and also release stars from here. So basically the structure we start with is indeed retained in the structure of the charcoal. That's why it's important to select the right feedstock to get the type of charcoal that is performing the work we have in mind. And in case here you see hardwood and softwood, the dimension and the type of channels is very different. And if you see through a pore analysis, which is done with mercury porosimeters and beta analyzers, you see that the volume intruded in the hardwood is much higher, and in average the surface available in the softwood carbonized is higher. For our scope is much better having a good volume intruded in the char with large pores, so that the stored moisture can be retained. Same from for the nutrients like nitrogen, and then slowly released in the soil for the benefit of the crop. So clearly, if we want to have a good biochar for our application, we have to take care of feedstock, of the technology, and the process condition we operate this technology. This for the impacts on the agricultural system. Indeed, if we only look at the amount of carbon we sequester from the atmosphere, well, actually, the only parameter that really counts probably is the fixed carbon amount you can measure on the charcoal. All the rest are of secondary importance. But what we think is that indeed, while you do an excellent job with biochar to remove carbon from the atmosphere, you can at the same time do a very good job to support agriculture. So it's good to try to get the best possible biochar for the application you have in mind. So which are the inputs? The increased moisture retention capacity. It's like a sponge in the soil. You can limit leaching of nutrients and thus to incorporate and slowly release this nutrient to provide a suitable habitat for microorganism growth. And then on the surface of the charcoal itself, on the pore surface, you can have high reactive surface depending on how, again, the biochar is produced, and have reactive functional groups, hydroxylic groups that affect the carbon and the anion exchange capacity that have a role in the nitrogen cycle in the soil. Indeed, another parameter that I have no time to go through today is the size. We have two effects in the soil from biochar. One is related to the intraparticle dimension, and one is related to the interparticle dimension. The interparticle dimension means the size of the particle of biochar that you put in the soil. They affect the average soil porosity. And the other one, instead, the intraparticle, is what I was showing now, is the porosity of the particle itself, internal to the particle of the biochar. Depending on the type of soil, you need different size of interparticles, because for instance, with clay soil, you need to improve the flow of the moisture in the soil, while with sandy soil, you need to avoid water to flow through the soil downwards and to lose in the first 30-40 centimeters the availability of the water. So in that case, it's preferable, in average, a smaller particle, a very porous charcoal, while in the other probably the particle size should be greater and have a better interparticle distribution. Again, it's related to the specific site. Regarding reactors, as I said, is known since centuries. So kilns, retorts have been developed for so many years that FAO knows very, very well this topic. There are also industrial technology like converters here. I will show these components, for instance, rotary drums that are probably the most appropriate for this. There are also advanced technologies like fast pyrolysis, reactors that probably are more prone to be used for liquids rather than solids, in the sense that the main goal is to produce a fuel, a liquid fuels or a biocrude to be upgraded then to liquid. Charcoal production, as said, is known. These are examples of traditional systems. Please have a look here to this pyrogases being released from the pyrolysis volume. The same you can easily see in European technologies, traditional technologies here. This is all wasted energy. And exactly what we say, where you can get this high temperature renewable energy to make it available. That's not only, there's a second point, you are losing energy, but you are also polluting dramatically the environment. You see how here is so black from charcoal deposited, but also from tar and water with organics that is condensed. You see the atmosphere is very polluting, is unhealthy for the operators, is bad for the environment. So it's a lose-lose option. We are losing energy, we are polluting the environment. That's why industrial technology have been developed in many years typically for charcoal making for two main applications: barbecue charcoal and also steel charcoal for steel making plant for eucalyptus, for example. Brazil is producing charcoal for steel making plants. However, our goal is slightly different, and our point is the product has very low value for us because it goes in the soil. I have been invited by FAO in 2007 to speak at this workshop, and I have downloaded recently this work that is dated 2017, 10 years later. So FAO is very familiar with charcoal, but still the main focus here is to produce a product that is indeed renewables, but it's used as a fuel, which of course it is a case. But what we're talking today is about using this in the soil, and it's quite different under many point of view. These are examples of technology. I wish to spend a few words on that. These are some of the one we have available in our lab. This is a rotating kiln pyrolyzer, 100 kilogram per hour feed in. It is completely resembling a full industrial scale plant. It by itself can also be quite industrial scale. This is a 50 kilogram per hour fixed bed and not moving bed reactor, which is also oxidative. In that case of the rotating kiln, it's completely anaerobic. In that case, we use a bit of oxygen to deliver the heat to the reactor itself. Why we do this? Because this is much lighter, much less expensive. It has some constraint regarding the type of feedstock that can be used at the inlet. Rotating kilns are perfect to be fed with any type of organic material, while this fixed bed are more challenging regarding the feedstock, but on the other hand, it's much cheaper. Would say a third of the previous technology. At that scale, you can consider the cost can be some 300,000 to 400,000 euro for the rotating kiln, and probably 100 to 200 for the second one below. I mean, produced here in Europe, by the way. It could be probably industrialized, and cost could be further reduced. Then there are other types of pyrolysis on which we're working. There are intermediate pyrolyzer, like the one you see on the top right hand, and there's a new one coming, a bit delayed because of coronavirus each impact on our suppliers, but is a nice integration of these two. It will be an auxiliary, let's call it moving bed system that would aim at representing a compromise between the two, trying to get the benefits of both. As said, the feedstock and the process parameters are key to get the quality of the biochar product. And the products differs regarding pyrosity, organic carbon and ash content, stability, pH, functional groups on the surface. I will not spend time to talk about the liquids, but just let me make this flash note. Condensate has been used again for centuries as a biocide, biostimulants, biofertilizer. It's difficult to use it today. It was called wood distillate, and there are still countries like in Indonesia, if I'm not wrong, Thailand, where this is still commercially sold. To our view, it's a very interesting additional part, which can be very well done. It is rich in acetic acid, it is organic, but indeed to meet modern regulations, modern standards for biocides, biostimulants, biofertilizers is a challenge, and R&D is needed more than from the technological and process point of view, from the regulatory and norms point of view. But I would recommend to keep an eye on that because it's really interesting. Second point, it can also be well integrated with anaerobic digestion in the proper amount. So summarizing, biochar acts on physical, chemical, and biological properties of the soil through aeration, porosity, and mechanical structure and moisture retention, the physical, through pH modification, carbon-ion exchange, impacts on nitrogen cycle, addition of carbon recalcitrant that can be a suitable environment for microorganisms, and to incorporate and slow releasing nitrogen, reducing leaching in groundwater, and also as N2O in the atmosphere that we know is 320 times more greenhouse gas than CO2, and of course biological properties. It is highly stable in carbon in soil. This is a study among many done by Professor Kutsiakov, published some time ago, 2014, that very well demonstrated that if you produce well your biochar, and let me stress this point, many times we see works that address agricultural works without any discussion of what they have in their hands, the characteristics of this biochar. You indeed need both in your analysis, but well, Professor Kutsiakov clearly showed that at least hundreds of years are really stable for this the stability time for this biochar. And what you see on the bottom left hand is the IPCC, and again you see that if you produce biochar at the right temperature from the right feedstocks, it can really stay there for hundreds of years. Most likely, the moment it will be dedicated, our agriculture, but also our energy system will be completely different. Anyway, IPCC specifically addressed that in their report on global warming. There was a chapter dedicated to biochar. Then there was a much more and wider discussion in the report of climate change on land that was 2019, 7th of August, to be precise, and it given the GHG abatement potential, reviewing a large number of studies, and even more important, as shown by Johannes Lehmann in our latest conference in biochar, they have provided the guidelines to include accounting of change in biochar carbon stock in mineral soil receiving biochar addition. That was a really important point because guidelines are revised quite rarely. The previous version was from 2016. The new one is now 2019 it was released. So we have a completely available framework to address this issue. It can therefore be used for offsetting greenhouse gas emission. Technology is mature. Every ton of CO2, of carbon, I remove 3.67 tons of CO2. It's very cheap, and I will come to this in a second, and at the same time promote more sustainable agriculture. Basically, taking the example of sustainable aviation, 1 ton of kerosene contains roughly 1 ton of carbon. 1 ton of biochar roughly contains 1 ton of carbon. So it's 1-to-1 comparison. 1 ton of kerosene, the cost today, we coordinate one of the largest projects, is around 1,500 euro per ton. The cost of 1 ton of biochar, which also deliver other benefits, while the biojet's not, is roughly from 200 to 500 euro per ton. So it's roughly 1/3, 1/4 of what we're saying. And it generates consensus also in the farms and in the farmers. It can support rotations, agroforestry, the biogas done model done by our colleague of Italian Consortium Biogas, and that Bruce Dale presented in a similar webinar here at FAO. It is perfectly integrated with 4-per-mill initiative, or as I said, with agroforestry that was discussed some months ago in a GBEP meeting in Rome. So it's perfectly compatible in scale and systems with these approaches. What we do is to produce a co-composted material with organic matter from the anaerobic digestion, from digestate. We start from observing that only the European Mediterranean region, 7 countries, has already clearly 8.5 million hectares under marginalization because of climate impact and desertification and dryness. It's dramatic. This is documented by JRC in the World Atlas of Desertification and other studies in the framework of H2020 European project like Stubian. So there's a lot of evidence in that. So we are targeting these areas. It's large enough. We have published this work, so you can download. I don't spend time on details. You can find all the details of co-composting here. Biochar can enter the anaerobic digestion process in many points, in the feedstock, in the reactor, in the gas stream, and with the digester. We are focusing on the digestate, but we did not just blend. We co-composted the digestate with biochar. And this is done also in other places. This is from the Biochar US initiative, and you see also similar things. This is what we have done in our small plots, and we have observed that composting is slightly accelerated. The temperatures are slightly increased. The nice thing is that, especially if you have a not so much controlled anaerobic digestion process, that can be helpful to control proliferation of microorganisms like Escherichia coli and others. This is our project, and I will show the first preliminary impacts. We took 2 areas in Spain, very dry, very poor soil, extremely low moisture. We have replicated 4 times 7 different cases, no fertilization, 10, 15, 20% combi biochar in compost, co-composted, 100% biochar and fertilization, and 100% compost. And you see it's quite visible in the early stage of camelina. Camelina is grown there because it produces an oil that is suitable for biojet production. And you see the impact is quite interesting. From the agricultural point of view, it's interesting to observe that this field would have produced nothing at all in this season unless we do this kind of intervention on the soil. So this year, for instance, we are carrying out a rotation with barley. So this soil is brought back to production for both the benefit of food, feed, products, and energy. And it can also deliver economic resources from the energy efforts, from the energy directives. For example, this land is clearly to be classified as low ILUC land. And we have a measurable system to demonstrate our intervention. It's like a capex in that case. We invest over the 2 years to inject in the soil our products. They will last for decades at least. And so coming to the last part of the presentation, the remaining slides, we are moving from a very linear model that resembles the oil making approach, feedstock coming in, processing, delivering and using, and then asking, are we sustainable enough, to a completely different model in which it's multi-feedstock, multi-annual rotation, cover cropping, BDR, 4 per meal, multiple products and multiple markets addressed, and then having a real circular. And then we say how this system makes conventional agriculture that relies on fossil even more in the most difficult areas to become more sustainable. We don't have to forget that more chemical derived from fossil are used in the most difficult soil, and more of this is lost in the groundwater and in the air because of the low quality of the oil that doesn't keep this into the first 30, 40 centimeters of land. So circularity and bioeconomy integrated in rotation with protection of the land for food and feed and other products. That's what we believe. So this slide is basically summarizing what I say. It's the moment to move to a very highly interdisciplinary field, which is for a country like mine, Italy, is probably one of the biggest challenge. We tend to operate in separated rooms, each one specialist in his field, and hardly speaking to the guy in the next room. And that is a very old way of treating complex and holistic problems like this one. And it, this approach is hiding the big potential that we can deploy. Regarding Combi, of course, the question is, does it pay off? Well, actually, this depends on the policy that is in place. Of course, there are environmental benefits. That's clear. My point is, it is worth in terms of economic returns, and this depends really on policy. Again, for example, in integrating with anaerobic digestion, it depends on the quality of the digestate, for example, on the healthy and safety issues there. That's an example. So it has to be evaluated case by case. Biochar is not a solution which remains equal for every place, every agriculture, every agroclimatic condition, and every policy applied in the specific region, but it has to be addressed separately. But like biogas, is a perfect integration in a small-scale biorefining project, bringing economic return and social economic benefits to the rural communities. And we have to recognize that GBEP, that Michaela was mentioning before, has been the very first to see the sustainability under also the social and economic criteria, and not just the environmental, that, to my view, of course, is absolutely essential, it's very important, but it's a very limiting and narrow point of view. We have to apply this kind of approach like UN SDG are doing now. We also started to investigate policies at the European level to support, and we found actually policies already there, but policymakers are not aware or are driven by other considerations. So existing resources that in Europe are very large for the common agricultural policy are not yet deployed as they should to support environmental action done by the farmers, as instead they require. So concluding, it can play a really important role under many points of view, not just carbon negative action, but also in many other fields. So it has an advantage, a very clear advantage compared to carbon capture and storage, for example. To me, there's no level playing field because we deliver also benefits in the same time we remove the carbon. The other are only addressing removal. Maybe carbon capture and utilization can be something that can compete with biochar. It can deliver renewable energy and bioproducts at the same time for many different applications. So it's also a way to secure this business, because who's producing biochar can also produce at the same time charcoal as a fuel, for example. We all know charcoal pellets, charcoal briquettes. That can be very well done. And it's the same type of plant. So you have a diversification of the business of the economic operator, which is another good point. Thermochemical and biochemical must be integrated in future CISA, and to my personal view, would be very good if we can integrate at farm scale. That's why I appreciate collaborating with the biogas industry, the Consortium Italiano Biogas, and thereby by BDR model, because we really believe this kind of integration between thermo and biochemical brings mutual benefit. Of course, policy has to follow, but it was the same when the biogas and RIGHT started and biomethane initiated to be discussed. Then a policy came. We need to reach that point. And there are other areas, for instance, on condensates that will offer other opportunities to substitute biocide and biofertilizer and biostimulants from the chemical, fossil chemical industry. As I said, supports sustainable agriculture. My last and most important remark is about the economic value of this carbon. Let me conclude with this recommendation to all of you that can have an impact on the policy making. If I produce biodiesel, if I produce bioethanol, if I produce biojet, I receive in different form support. I have in America you have RINs, renewable certificates. In Europe you have mandates. In course you have obligation. There's also emission trading schemes for airlines or for other type of industries. If a farmer deliver a much higher benefit and store carbon, sequester carbon, and improve the soil, there is no recognition to the value of this carbon. So my recommendation is, let's bring, and I conclude with that, the discussion to how to have this value of the renewable carbon that is sequestered and brought back to the soil, reducing the impact of climate change on agriculture, can be recognized to the primary sector, to the farmers, improving their socio-economic condition. That is perfectly in line with SDG, and the work could be supporting enabling sustainable agriculture through biochar. I thank you for your attention, and I'm open to discuss any question you may have. Thank you.
Thank you very much, David. Thank you for this very comprehensive and clear overview on the biochar realm. We very much appreciate it. We have more than 90 participants. And I have to say that you have very well highlighted the one that I think is the major added value of biochar, or the fact that it is flexible. The biochar production process and the application to soil is flexible, and this flexibility could be exploited to adapt it to different type of context, different type of local context, for instance, different primary needs. There could be somewhere in which we need more energy, in some place we can need more biochar as soil amendment, in some other place we can need more biochar for carbon capture and storage. And I appreciated a lot the IPCC special report has highlighted the key role of biochar as a means for carbon capture and storage. So I would like now to open the floor to our participants for their question. I will pick and choose some questions from the chat based on the fact that, as Connie has already mentioned at the beginning of this webinar, the agronomic aspect will be discussed and clarified in the next webinar of this series that will be held at the beginning of June, thanks to the collaboration by Professor Johannes Lehmann. But let me now take some question, and maybe we can dedicate the remaining time to answer this question. The first question was related to the cost of biochar, and if you see that it is suitable and is convenient, and what are, I mean, we would like to know from you what is the amount that we can put into the soil, what is the range that should be respected in order to have the effect, to can measure the effect, and what is the cost for production and for distribution, let's say per hectare. But it's the issue here is not a solution that is too expensive.
Yeah, it's a very good point, and it gives me the opportunity to show how the policy has a huge impact in very different way. Let's compare, for example, for our colleagues to know, the Common Agricultural Policy supports farmers per hectare, and the decarbonization measures in energy supports per ton of carbon, basically. You understand that when we talk about cost and the amount that is deliverable per hectare, this has a huge impact. Let's start with the cost of the biochar in industrial scale systems. So clean production of biochar, first point. Our estimation is that if you start from residues, and then we will address this point because I see in the chat some question about that point, but if I use as feedstock residues, I can stay probably in the range of 200 to 300 euro per ton. And if I go to more focus and better quality feedstock, in the sense that even if residual, these are more selected, maybe it will cost something between 400 and 500 euro per ton. So if I am paid by the decarbonization policy per carbon, the amount I deliver in an hectare is irrespective. I mean, my point will be, is my business sustainable with this recognition per ton of carbon, as it happens in biodiesel, bioethanol, biomethane, all these things. If instead, as it is done by the agricultural sector, if it is paid by hectare, then I'm very limited. I guess you cannot put more than 2-3 tons per hectare. In the study we made with Poppy, that is referenced in the presentation, you can find our first model on that, and clearly you are limited in the amount. So that's the first point. The second point regarding cost, let me make an example. If you build a house, you do not pretend to pay the mortgage in a year. No, you have an amortization period of 10, 20, whatever it is. What is happening in the way agriculture is supported today is that these are yearly measures. These are measured over 1 year. No, so what I'm saying is that the action you're doing with, like a building, when you build your house, will last for many years. So, for instance, if I spend 1,000 euro per hectare, just to make an example, it's illogical. It's an illogical thing that I pretend to be repaid in 1 year, because my effect will last for a very long time. So it's a different way of thinking. This kind of things are the most difficult to be modified, because you know, the policy makers and all the market is structured on a different way. But it doesn't make sense for biochar. You have to think like a long-term investment that the farmer is doing for the benefit of everybody. And so it's a mix of things.
Thank you, David. Thank you very much. We have other questions regarding more the environmental aspects, and in particular the greenhouse gas emissions. I mean, of course, compared to the traditional kilns that are used in developing countries, we don't have, I mean, there is no discussion. I mean, it's of course to reduce the greenhouse gas emission, but did you have an idea of an LCA approach done, for instance, by using agricultural residues or woody biomass compared to the business as usual for energy production?
Okay, I see there are a number of questions on that, and then there's one on the carbon market certification, which is a different thing. So let's start from the environmental. Well, more than environmental, my understanding is that on the feedstock sustainability of the feedstock supply chain, which is a more general point of view. I'm a thermochemical guy, not a specialist of LCA, but let me remark the key points of that. First of all, and this has an impact on the reactors. As I said, for example, rotating kilns can very well work with any type of feedstock. We do have a lot of agricultural residues that are available already and that are not used. In some cases, I remember a long time ago, they were even burnt in the field. Probably now it's not done anymore, but this was a typical issue with China, for instance. So these residues are available. Of course, you have to compromise and to accept the quality that will be the best possible with this type of feedstock. You have to select reactors that can cope with this feedstock and probably accept multiple feedstock. That's one example. Then another example, in Italy, we do not cut enough the wood that is grown every year. This is well documented by many works done by Professor Bolsonella, and you can find a lot of literature. So there can be cases like Italy in which we do not use the amount of wood that every year the additional amount is grown, and that's another possibility. Another point is agroforestry. You could very well use fixing nitrogen woody species that are good to produce biochar, that inject nitrogen in the field among agricultural rows, and that can be cut and regrow on the same field, and that is perfect feedstock for biochar. I remind you also that compared to charcoal, biochar has a much smaller size because also of the effect it has a lot to do with the surface to volume ratio. So pieces are in average smaller. Charcoal is done with bigger pieces. So it very well cope with residual material and small parts of these residual materials. So actually, I think we are very far from any issue in being able to provide sustainable feedstock. My point is that, of course, the supply chain must be controlled, must be monitored, possibly must be even certified for the largest chain, to ensure that we are using the right portion or we are adopting the right agricultural model so that this can be delivered. But I do not think that we lack feedstock material that can be sustainable. On the contrary, some of the feedstock, like in agroforestry model, can be quite beneficial for the agricultural field. So I really, at this moment, I really do not see an issue on that.
Okay, can you add something on the scalability of the process? I mean, for instance, how could it be affordable for poor people, and if it is scalable, or for people that have a low, contained amount, I mean, a reduced amount of biomass?
Yeah. Okay, I also quickly respond to Damien. No, it states centuries. You can find literally even millennia, but I mean, centuries is quite long enough, I think, to remain in the soil. Regarding scalability, this is a very nice feature of pyrolysis. Compare, for instance, to gasification. You understand, pyrolysis has been developed for many, many years. It can, it doesn't require sophisticated gas cleaning system that instead are necessary for gasification to feed the gas to an engine or a gas turbine. So, and then I have to connect to the grid. So I need to have the grid and I have to pay the connection, which is a quite expensive component of the investment. If you go for pyrolysis, all these things are really not needed. I pyrolyze, I get the pyrogas which I can burn, or in case condensate if I find a nice application for the liquid. And then I have the solids. That's it. I don't have grid connection. I can build this, you have seen, from 100 kilograms per hour to easily 5 tons per hour, which is quite big. It means 2 tons per hour biochar coming out. Without any particular problems, with many different reactor technologies that have been widely demonstrated. That brings me to another advantage, the bankability. We mostly focus on technology or science, but you have also to consider that the bank will require documentation, will require recording of performance to deliver the financial cash flow to implement the project. In the case of pyrolysis, we have a lot of opportunity to demonstrate that we are actually using a mature technology. Maybe we can improve, but we start from a paper that is very, very much documented. It's very much demonstrated. So there is no financial risk if well controlled and documented.
Okay, thank you, David. I would like to pick up last question from the chat, and then I will open to the participants to raise their hands for a quick, very quick question. So the last one is the one of Esrag. How is the pyrolysis gas captured and managed for secondary use so that it becomes a useful product, not polluting emissions?
Well, actually, when you have the pyrogas, actually in the volatile form, I go back to this slide, you have 2 products. One is the liquid in the form of vapor and one in the form of gas. If you decide to go through condensation, in dedicated apparatus, you can condense the liquid. The liquid then separates in 2 phases. The main is a water phase, but main means more than 95% is what is called water distillate, is rich in acetic acid, and it can be very interesting for many applications, but there's R&D to be done there. The gas remains clean, and then you can exactly produce electrical energy at that point. You can feed to an engine and generate electricity, which is a value for many places, especially in third countries, but also in developed countries, because this is fully renewable energy that is supported by public measures. So actually, we do not do this yet, unless at research level, because there is no clear rules for norms and standards to use this liquid. As in many cases, modern rules and standards are much more complex than the older ones. I could make an example. In the algae sector, we have only 2 algae that are eligible for food, which are spirulina and chlorella. there's a working group in Brussels working on many other algae that are very good indeed, but modern regulation that were not in place at the time of spirulina and chlorella recognition, and this requires a lot of work to be marketable products. The same thing I think applies here. In the liquid we have a distribution of many products, predominantly water and acetic acid and methanol, but there are others. So compliance with the different classes of fertilizer, biostimulants, biocides is complicated, at least in Europe. In Indonesia, I have seen that this is sold in the market, so probably is a different situation. It has to be addressed case by case, but I think it's a very important way to go. In that case, the gas is cleaned and can be used as a renewable energy carrier for electricity production.
Okay, thanks a lot for your patience. And David, we have a first raised hands by Valer and Zeimana, and I would like to give the floor to these participants for a quick question. So don't be shy, Valer. Can you unmute your microphone?
If you're having problems, you may need to click the microphone button in the top of your screen. The microphone needs to be green.
Okay, it seems that Valer has some problem. Let's wait just a few seconds. Okay, let's move ahead. If someone else has some other questions, maybe you can raise your hands by clicking the button that is close to the microphone, is on the right of the microphone. Nobody else, so it seems that they are... okay, we can go ahead. Maybe we can pick up another question from the chat while people are...
there was one, Tiziana, about literature on LCA. Yes. There are many works in this area, but I think that the best thing, you go to the IPCC report, the one that I showed here, because these analyses have already been digested there, and so here, okay, this one. So if you go on this report on climate change and land, you will find this kinds of analysis, and it's already, I mean, it's already digested, let's say, if I may say.
Yes, indeed, this is the last special report on climate change and land that has so yes, has so many chapters dedicated to the various benefits of using biochar. I can see now that Valer has unmuted the microphone. Maybe wants to say something. No, yeah. Probably we have some technical. Oh yeah.
Yeah, Valerie. Yes. Anyway, is about cutting trees in Central African countries. Absolutely, yes. As I said, if we know the shape, the type of biomass that is available, and it can be of many different types, indeed, the remaining part of this huge tree, assuming that it's sustainably cut. This is not my job. I don't enter into the point whether it's sustainably done, this cutting, or not. This belongs to other people. But assuming it is, indeed, any part of the tree, for instance, in case of Italy, we normally use logs below 10 centimeter diameters. then you chip it and you use it. That's it. Absolutely doable. While for other application you have more stringent constraint, and this is more difficult to be done. And also to answer Federico demand, yes, you can pyrolyze almost anything, even liquids. So even the organic fraction. The point is if it is worth to do or not. It's questionable because you have readily available organic materials and nutrients, but technically speaking, we have done and we have observed almost 50% of the nitrogen remaining in the char after charcoal making.
Okay, thank you, David. Let's see if someone else wants to raise his hand, some other participants. Okay, I can see now Olivier Dubois that is raising his hand.
Yeah.
So please, Olivier, can you unmute your phone?
Yes. Do you hear me?
Yes, perfectly.
Right. I think most people they won't disagree with the potential advantages of biochar. But I think the crux of the matter is then why is it not implemented more widely? And I see at least two issues. One is if you start growing trees and crops dedicated to biochar, because you need a lot of feedstock, then there's a potential issue of two things: competing use of residues and other uses of the feedstock. That's one thing. The other thing is basically what was already mentioned, is the sheer cost. I mean, I don't know, David, how many tons you consider per hectare, but if you consider 20 tons per hectare, then we should be around $3,000 to $4,000 per hectare. And that's a lot. So when you set 500 maximum and in small using residues 200 or 300 euros, because of the limitation related to the cost, then what impact do you have with such a small amount of biochar? Thank you.
Okay. First, nice to hear from you, Olivier. Very good intervention, and that's why I added some slide on aviation. I will go step by step. Well, first of all, if the payment comes from the carbon you sequester, the amount you deliver per hectare is irrespective. There's no link. Every ton I receive a payment, no? Do you want to see an example of that? Very simple. The new CORSIA program on jet fuel, the new CORSIA program already include offsetting, and this is paid per ton of CO2. Just to be practical, today ETS value is some 24-27 euro per ton of CO2, which means 3 times more for the carbon. Only with this measure we are some 100 euro per ton already. So if the biochar cost is 200, for instance, because you produce from residue, it's already good. Second, the project that is on the back still is on aviation. This is marginal land, and we do have 8.5 million hectares only in Europe. And this feedstock is needed by the industry, and it has a high value. So what I'm proposing is try to bring the fuel producers, like in that case in which both European Commission, JRC, and Total are participating, try to bring them on board of this kind of project, because they support recovering of land that is in very bad shape, and there's a large amount of that, and they can deliberately release some of the resources from the obligation in the energy sector. That is another point. Third point, common agricultural policy. Farming has now, in the revised common agricultural policy, mandates to contribute to decarbonization. This makes me think that you should be paid per ton of carbon you remove and not per hectare. It's meaningless, the payment per hectare under that point. Another work to be done. But to me, CORSIA, if I may say, is the first immediate topic one could address. But indeed, if you expect that oil company or airlines are familiar with this concept, you are going too far. It is the agricultural sector, organizations like, I don't know, FAO, JRC, whatever, that show how this can be a farm-scale technology, can be well implemented. Regarding the impact also, I forgot one point. If you, let's do this exercise. Cardoon is cultivated for biopolymers. Novamont, for example, is doing this in Sardinia to produce oleic acid for Mater B biopolymer. Okay, how is this kind of cultivation done? That you have addition of compost in the soil over a certain amount of years, let's say 7 to 10 maybe, something like that. So it's not necessary that I immediately put 15 tons of biochar. I can start with the first 7, 8 years adding, I don't know, 3, 4 tons per hectare plus compost. Then after 10 years, I go back to the field and I add a bit more and I continue for a limited number of cycles. So it's like having 3 times more the land. But again, it all depends on why this carbon value is not recognized to the farmer and is paid to the oil company. If you consider how much is paid biodiesel and biojet and bioethanol, biochar has 0 value, and it brings more benefits to the environment than the fuel. I work on fuel, so I'm happy that sustainable biofuels are produced, but I cannot deny that biochar brings more advantages and not less. And this carbon is not valorized. So the problem is political, to bring this to the attention of the policymaker. That's my my view. And another point is that it can be for the business operator at the same time a plant producing charcoal for other uses with very high value where is needed, and biochar for the soil when there is no demand. So unfortunately, I do not see the possibility to deliver one solution for all. I think that, like the question about Central African countries before, I think we have to go place by place and sites study the right conditions for the specific place. I can also answer Lori very quickly. Hydrochar is a completely different thing. We do produce hydrochar that comes from hydrothermal carbonization, not liquefaction. We work at much lower temperature and pressure for carbonization. But if you see the carbon content typically exiting the process in the hydrochar is slightly above 50%. In biochar and pyrolysis, our fixed carbon content goes up to 90%, depending on where we want to go. And the porosity is completely different. It's much, much more porous. So hydrochar can be used as a way to dry very wet biomass and then to be processed into pyrolysis. What we're doing now, or considering to do now, with wastewater sludge from urban wastewater. But the difference is very, very high, so the carbon benefits also are very different. Hydrochar has a lot of labile carbon. It's something that can immediately degrade. Just to explain, means that we are in that part of the curve. We're here. So we have very quick degradation if the carbon is not fixed carbon.
Thank you,
Okay.
David. We would like to pose to you many other questions, but unfortunately the time is going to an end. And I just want to thank you very much for your availability and for presentation that was very clear. We will send you a list of the other questions in case you be so nice to answer them, okay. And we can put these your answers available on the Global Bioenergy Partnership website, as well as the recording of this webinar will be available on the same page in which was published this webinar. And I would like also to say that, to highlight the fact that we as a Global Bioenergy Partnership usually assess the sustainability of the bioenergy value chains by going through adopting an LCA approach. So we will go usually through by analyzing the processes and also but also the biomass production, not only the technology, and finally the use of the bioenergy product itself. And this is the main reason why the next webinar on biochar will focus more on the biomass production, on the interaction of biochar with plant, soil, microorganism in the soil, and with water in the soil, and will be held at the beginning of June by Professor Johannes Lehmann, and we also will treat about the biomass supply and demand. We will better answer to the question that Olivier has raised, and also looking at biomass demand and supply in at the sustainability of these in developing countries. Now I would like to thank all the participants and briefly leave the floor to Michela Morese, the Secretary of the Global Bioenergy Partnership, for a final and closing remarks. Thank you, David, and thanks to you all.
Thank you very much, Tiziana. Yeah, so just a very final, let's say, consideration at the end of the whole presentation of the question and answer, and the general consideration regarding the role of bioenergy and the role of biochar that has also been questioned in terms of if it's so if the effects are so positive, why it's not used so much. Sometimes it's in the way of thinking simply of people, and so we are aware that so far bioenergy and even more biochar have been somehow the overlooked giants in terms of renewable energies, but hopefully there will be a new consideration of bioenergy and including biochar in the future in terms of contribution to climate change, in terms of contribution to NDCs, INDCs, SDGs, as David was mentioning also. In particular, thinking about the IPCC report that David mentioned, the one on climate change and land, which was issued last August. And if we think about an article that has recently been issued, an interview to the UN Secretary General, that says that UN wants to reboot after the crisis, after the pandemic, with the reboot to be green. That has to be green, and bioenergy has a role to play in that context. So let me thank our friend David for his kind availability, for the very interesting presentation and the amazing exchange of question and answer with our participants. Let me thank all the participants to this webinar, and I hope to welcome you all again at the next GBEP webinar. Thank you very much. Thank you all.